Hi folks, we're going to take a look at number 23 on page 158. So we've got a rectangular garden that's going to be surrounded by a brick wall on 3 sides and a fence on the 4th side. And the area of the garden is 1,000 meters squared. And the cost of the brick and the fencing is different. So the brick is more expensive. And they want us to find the dimensions so that the cost will be the lowest possible. All right, so let's draw a diagram here. So I've got 3 sides that are going to be brick, and then I've got this 4th side here that's going to be fencing. All right, so if I call this X and this Y, I realize that in terms of brick, I'm going to have 2Y plus X meters of brick, and then I'm going to have X meters of fencing. Okay, so that's going to allow me to write a formula for the total cost of the materials here. Okay, so let's see what we have. So we have $192, okay, times the total length that I'm going to be building in brick, okay, which is going to be 2y plus x. All right, and then I'm going to add to that $48 times the length of fencing that I have, which is just going to be x, so plus 48x. So here's our model. Okay, that gives us a total cost. You know, often, as is often the case, we've got 2 variables, so we're going to have to find a way to fix that. And that's where the constraint comes in, that the area has to be 1,000 meters squared. So the area of this garden is just given by x times y, and that's equal to 1,000. And so from there, we can isolate either one of these variables. Now, I guess I would say that because x appears twice, that's not the one that I want to isolate. I'd rather just isolate y since it only appears once. So we'll write y as 1,000 over x and then do our substitution here. So the cost is 192 times, I should have probably distributed this here. So 2 times y, which we're writing as 1,000 over x plus x, and then plus 48. X. Okay, could have probably saved myself some time here, but let's do this. So we've got 192 times 2, so that's 16. So this is going to be 384 times 1,000, so 384,000 over x. Then here plus 192x plus 48x. And so we can simplify that a little further. So 384,000 over x plus, and this is going to be, looks like it's 240x. All right, and there we go. There's our model. Now here, I don't think there's too much we can say about the variable other than it has to be greater than 0. All right, so I see that I don't have a closed interval, so I'm going to have to justify any optimal values that I get. All right, so let's take the derivative here. So again, this is x to the negative 1. So when I take the derivative, it's going to be negative my constant, 384,000 times x to the negative 2. So that's just going to go into the denominator as x squared. Okay, and then plus 240. Okay, so let's set this equal to 0. So I'm going to multiply both sides of the equation by x squared, since this is a rational equation here. So I've got negative 384,000 plus 240x squared. Okay, and so let's isolate x. Okay, so first I'll bring the 384,000 to the other side, divide by 240, and then take the positive and negative square root when I'm solving, but of course I'm not interested in the negative square root because x is going to be bigger than 0. So as an application type question, so I'm definitely going to approximate this here. So let's see what we have. Square root of 384,000 divided by 240, and that gives us 40. All right. So let's now see that this indeed does produce a minimum value. Okay, so we start at 0 and our critical point is at 40. So let's test it out. So let's put, I guess, 1 and, I don't know, 50. Let's test that out. So if I look at the derivative here, I'll take this version of the derivative. So if x is equal to 1, well, I have negative 384,000 plus 240, definitely negative. And then let's stick in 50 here, see what happens. So negative 384,000 divided by 50 squared. Okay, and then plus 240. Okay, and I get a positive value there. All right. Now, of course, this just tells me that I have a local minimum at 40. Okay, but between 0 and 40, the function is continually decreasing, and then from 40 on, there's no other critical points. Okay, this is going to be, doesn't change, it doesn't change, so the derivative doesn't change sign, so it means it's going to be continually increasing from there. So not only does this represent on this interval a local minimum, but an absolute minimum. All right, so let's go back and see what they were looking for, and it looks like they were looking for the dimensions of the garden. All right, so the dimensions would be, I guess x here represents our length, so our length is just going to be 40 meters, and then our width is just going to be 1,000 divided by 40. Okay, and let's get that. 1,000, probably could do this in our heads, but okay, it looks like it's just, yeah, we really should have done that in our heads, 25 meters. Okay, so just to recap here, get your diagram in, realize that you've got three sides that represent the brick portion of the exterior, and so we needed the two variables to represent that, multiplied by its cost, and then this variable x multiplied by its cost, and then just do, as we often do, a substitution to write the equation in terms of one variable. And then from there, don't forget that when you're not working on a closed interval where you're testing the endpoints, you have to justify that you indeed have, in this case here, an absolute minimum on that interval. Okay, that's it for this one.